welcome everybody. So today I'm going to talk to you about neutralization reactions. And if you notice in the notes, I skipped over buffers and indicators. But if I have time at the end of this video, I'll go back to that. If not, I'll do that as a final video. But tomorrow we're going to do a lab with an acid-base neutralization. The experiment that we do is called a titration, and I'll talk to you about that in the next slide. So what does it mean to undergo an acid-base neutralization? Well, a neutralization, it can be defined as an acid reacting with a base, forming a salt and water. So now we could have different kinds of acid-base neutralization reactions. You could have a situation where you have a strong acid reacting with a strong base, and in this case you will produce a neutral salt, and that's really where they get the term neutralization from. What's a common substance that's neutral? It's usually some kind of salt. So this is the most common type of acid-base neutralization that you'll see, where you have a strong acid and a strong base. You'll produce a neutral salt and water. The most common kind of acid-base titration or neutralization that you see with this strong acid, strong base is usually with HCl and NaOH. So when I combine these together, I'll get table salt, NaCl, and H2O. There's actually this guy who will mix together equimolar HCl and NaOH, and then he mixes them and then he drinks the product. I don't recommend that. I think that's a really bad idea. But you know, I've seen that video and I wouldn't try that at home. You could also have a neutralization where you have a strong acid and a weak base, or a weak base and a strong acid. So for example, if we were to have strong acid plus weak base, we would actually produce a salt that is slightly acidic. Now this is still considered a neutralization, but the salt that's produced has a pH that's a little bit less than 7. You could also have a situation where you have a strong, or a weak acid I should say, and a strong base. And in this case, you'll actually produce a salt that is slightly basic. So depending on the type of acid and base you use will determine what type of salt you actually produce. On the reagents, they really don't talk about acidic, basic, or neutral salts. They kind of just treat them all as acid plus base yields salt plus water. An example of a weak acid and a strong base neutralizing each other would be something like HF, neutralizing a strong base like NaOH, and what you'll produce is you'll produce NaF and H2O. In this case, it was a weak acid, a strong base. The result is a basic salt. If I gave you some NaF, the salt is a solid and you dissolved it in water and you measured its pH would not be 7. It would be slightly higher than 7, probably around 8 or 9. Now what type of reactions are neutralizations? They all fall under the same category of a double replacement. Now, how do we use neutralization reactions in real life? Well, if you've ever had an upset stomach and you have indigestion or heartburn, you could take something like Tums, or you could take something like Mylanta or milk of magnesia. All of those substances act as bases. They neutralize the stomach acid and it relieves the indigestion. If you have really severe indigestion and it's happening all the time, you'll take another type of medication. That medication actually will just inhibit your stomach from making so much acid, and that's a more long-term response to this. That's something like Pepcid AC or something like Prilosec. Okay, so these are the basics for acid-base neutralization. You have to know how to write the reaction, how to form the products. You always produce one kind of salt and water. Now the technique that we're going to do tomorrow is called titration. Titration is a technique that's in the lab where you're actually doing a neutralization. And the purpose of this neutralization reaction is to sort of figure out what the concentration of either the acid or the base is. So you'll be given some kind of information about how much acid and base there is, but you'll have to figure out the concentration of either the acid or the base. When we do the lab tomorrow, you'll see that we're actually going to find the concentration of the base. We won't know what the concentration of the base is, and we'll have to determine that based on the concentration of the acid. So now, when we have our neutralization, when we write it out, if you look back up here, we had a balanced equation, HF and NaOH, HCl, NaOH, and when you neutralize completely, at that point, you've reacted stoichiometrically. You have equal moles of H plus and OH minus. Now we know that molarity is equal to moles over liters. So we can solve for moles. The moles are equal to the molarity times the liters, or the volume. We could use milliliters as well. And so this means that the molarity of the acid times the volume of the acid, since it's equal to the moles of the acid, will be equal to the molarity of the base times the volume of the base. And so now we can use this equation, and the formula will look like this. Molarity of acid times volume of acid times the number of H plus ions, and I'll talk to you why I do that in a second, equals molarity of base times volume of base times the number of OH minus ions. Now why do I include this extra part here, the number of H plus and the number of OH minus? That's to account for the balanced equation. When I say number of H pluses, what I mean is, let's say that you have something like H2SO4. That would have two H's in it. Let's say you had something like CH3COOH. People might look at this and say, oh, you have four H's. But in reality, only one of the H's forms H plus ions, and that's the H right here. So when you look at the acid and bases that are being used in the practice problems, make sure that you account for the number of H's that are in the formula. For bases, it would be NaOH, for example. That would have one OH, or maybe something like calcium hydroxide. That would have two OHs. So you got to be careful and look at the formula. One year on the Regents, they had a multiple choice, and they were mean. They actually had H2SO4 neutralizing NaOH, and nobody took into account the number of H's in the acid, and a lot of people got that question wrong. All right, well, let's see how we would apply this equation to a problem down here. So now I'm given this key piece of information that it's a titration, and as soon as I see that, I know that I'm going to have to go straight from my MA, VA, number of H plus, equals MB, VB, number of OH minus. So now they say that I have 20 milliliters of KOH. So I see KOH, I know it has one OH. I see it's 20 milliliters, that's my volume. I leave it in milliliters, I can do that, because the milliliters will cross out on both sides. And they are telling me that this is neutralized by 10 milliliters of HCl. HCl is 1H, and that the concentration of the HCl is 4 molar. And then I see that I don't have the molarity of the base, and they actually ask me for it. What is the molarity of the NaOH, or the KOH? So I make that my X. Now I go through and I solve for this. So on the left side, I would have 40 equals 20x. And when I solve for x, I get x is equal to 2 molar. It's that easy. So go ahead and try the next one, number 2, on your own. Be careful with those h's and those oh's. Make sure that you account for those when you set up that problem. You don't want to miss that. Okay, let's see how you do with that one tomorrow. Let me just introduce the lab to you, and we're going to do this lab with something called burettes. We want to do a neutralization as accurately as possible, and so we'll use this device here in the lab called a burette. And the reason why we use the burette happens to be because it will very, very accurately measure an amount of volume, and you'll see what the burette looks like tomorrow when we actually do the lab. And so you'll fill up that burette to a certain amount. What's nice about the burette is that it starts at the number 0 and it counts upwards. So actually what you can see is that when you have the initial amount of acid or base, you can look at the top number and subtract it from the bottom number and actually find the volume of base or acid that you added. Now something else that we put in a titration is we have an indicator. So this setup right here, it looks as though we have our base in our burette, so our burette containing base, we are able to dispense that base into the acid very, very carefully. That's part of the reason why we do it through a burette. We can actually add drop by drop by drop. So we add that base to the acid. The acid is contained in the flask. It will have the acid and it will have an indicator. Now the idea is that you add the base slowly to the acid. You swirl the flask as you're mixing. And over time, what you will see is that there will be a persistent color change, and you know that you've reached the point in the titration at which you have completely neutralized the acid with the base. At that point, it is called the end point of the solution. From there, we can figure out all the information we need. For example, we'll know in the flask here, we'll know the volume of the acid. We'll know from the burette, we'll know the volume of the base. We will either know the molarity of the acid or the molarity of the base. So for example, maybe we'll know the molarity of the acid. Put a little check next to that. But we will not know the molarity of the base, and we will need to find that. We can plug the values into our MAVA equals MBVB, and we can solve for the molarity of the base. Now, one thing I want to show you on the burette that's important is how you take the measurement. Notice that the burette has 0.1 marking, so it goes by 0.1 milliliters. That means that you can actually make a reading to 0.01. And notice the reading that they have here is 39.31. That last one in the hundredths place is uncertain, but it is still included in the measurement. Okay, so we'll do this lab tomorrow, and you'll get an idea of what the experimentation looks like. And thanks for watching.